Hey everyone, this is Mr. Jacobs and you are watching lesson 1.2.3. So I have the ebook called open here. I think you should open up the ebook yourself using your Chromebook so that you have it in front of you. We are going to work through chapter 1, lesson 1.2.3. Lesson 1.2.3 says, what do they have in common? The family of linear functions. In lesson 1.2.2, your team investigated functions of the form f of x equals 1 over x minus h, where h could be any number. You learned that as you changed h, the graph changed, but the basic shape stayed the same. In this lesson, you will think about functions of the form f of x equals mx plus b. And question 198, question 199, question 100, and question 101 are the core problems that I want you to work through. So I want you to work through them in your teams. Again, that is problems 98. So the core problems are number 198 through 101. I want you to work through your teams, work with your teams to work through these questions. So pause the video, read the questions, try them on their own, and after you've had the opportunity to discuss them, or if you get stuck on some questions, then go ahead and resume the video and I will do my best to explain. So, question 198. Consider functions of the form f of x equals mx plus b. I want you to remember that mx plus b, f of x notation is the same as y equals notation. So we've got y equals mx plus b. And part A says, what do x and y represent in this function? What do m and b represent? Which ones can you change? Well, x and y are the variables. M represents the slope and B represents the y-intercept. So which ones can change? Well, you can change the slope and the y-intercept. So you can change M and B. And what we're going to do is explore what happens when you do change M and B. So with the rest of the class, explore the effects of m and b on the function. What effect does m have on the graph? What effect does b have on the graph? I want to show you something really cool that you can do with Desmos. So I am going to direct my web browser to desmos.com. I'm going to start graphing, and I'm going to type in y equals, I'm literally going to type mx plus b, and it's asking me a question. Would you like to add sliders? Yes, I would like to add sliders, so I'm going to click on all. And right now I see two new things have appeared. It tells me that m is 1, and it gives me a slider. I want you to watch the graph as I change m. I can make m really big, or I can make m negative. And as I'm changing m, look at the graph. What's changing? Well, the slope is changing. When m is positive, it's increasing. It's getting going up from left to right. And when m is negative, it's decreasing. It's going down from left to right. And if we set m at 0, then we have a horizontal line which is neither increasing nor decreasing. B, we can see when we set b to 5, it's touching the y-axis at 5. So b is simply moving our y-intercept up and down. If I change b to -5, now I'm touching the y-axis at -5. So with the rest of the class, explore what effects does m have on the graph? What does b do to the graph? Well, m controls the slope. We could say the larger m is, the steeper the line gets. Right here we have a very large m value. Here we have a smaller m value. And here we have a negative m value. And if we make one perfectly flat, now we have m is equal to 0. B, on the other hand, I'm going to put a dot here at the y-intercept. This is the point 0, comma b. So as you change b, this point just moves up and down. So for this function, m and b are called parameters, which is different from a variable. X and y are called the variables, m and b are called the parameters. With your team, explain the difference between a parameter and a variable. So this is part C. A parameter can be changed. Variables are your inputs, which are x, and outputs, which are y. Part D says, what do all the functions of the form mx plus b have in common? Since they all have the same basic relationship between x and y, they are called a family of functions. So what do they all have in common? Well, they're f of x equals mx plus b are all lines. They're linear functions. So the graph is always a line. Now, moving on to question 99. So I'm organizing my notes. So here's question 199. Part A. I want to look at each of these equations. It says, with your team, examine each group of equations below and discuss what you would see if you drew the graphs of the 4 equations on one set of axes. Write a description of what you imagine you would see. You do not actually have to draw them. Well, it's easier to compare equations if they're all in the same form. So I'm going to take 2x plus 2y equals 10, and I'm going to subtract x from each side. So I have negative x plus 10, and then I'm going to divide everything by 2. So I have negative 1/2 x plus 5, so that I have this first line in slope-intercept form. The second line was y equals negative 1/2 x plus 3, and I'm noticing something here right away. I notice that these two lines have the same slope, but that their y-intercepts are different. And I'm guessing if we divide this equation by negative 4, we're going to see the same slope again, because 2 divided by negative 4 reduces to negative 1/2 x, and 8 divided by negative 4 is negative 2. We see the same slope there again. And the last line is already in slope-intercept form. I could write it as negative 1/2 x plus 0. It has the same slope as well. So all of the lines are going to have the same slope. These are all going to be parallel. In part B, on the other hand, if we try the same thing and do y equals negative 5x minus 3, and we have y equals negative 1/2 x minus 3, and if we take the 3x and subtract it from each side, we'll have negative 4y equals negative 3x plus 12. And when we divide everything by negative 4, we get y equals 3/4 x minus 3. And on the last one, I'm going to add 2x to each side. And then divide by 5. We get 2/5 x minus 3. This time, it's the minus 3 that's the same on all of them. So if we were to graph them, we would have all the same y-intercept, but different lines. So this set will have the same y-intercept. Moving to question 100. Parts A through F below are 6 different representations of relationships that contain an input and an output. With your team, decide whether each relationship is linear and write a clear summary statement justifying your decision. If the relationship is linear, graph it and find its equation. If it is not linear, describe the growth. All right. Well, as you are looking at 100, what I want you to know about that question is that linear functions all have a constant rate of change, which means they have a steady slope. So if I'm looking at part A, which has a table that's representing pieces of bread and grams of fiber, I'm going to break it down to an X and a Y table. And as I look at these, what I am going to compare is the rate of change. So 1, 5, 2, 10, 3, 15, and 4, 20. What do I mean by rate of change? I mean the change in y divided by the change in x. So I am going to look for growth, and I see that I am going up by 5, up by 5, up by 5, and up by 5. At the same time, my x values are going up by 1. So my rate of change is like a rise over run. It's going to be the change in y, or how much the y's changed by, which we said was 5, divided by how much the x is changed by, which gives me 5, and the unit would be 5 grams of fiber per piece of bread. So 5 grams per piece. And because we have that steady rate of change, this is linear. Part B, Killer Fried Chicken, probably abbreviated KFC. Killer Fried Chickens charges $7 for a basic bucket of chicken and 50 cents for each additional piece. The input is the number of extra pieces ordered, and the output is the total cost. Well, let's make a t-table here. If we have our input is the number of extra pieces, and our output is the total cost, if we don't buy any extra pieces, then we just have the basic bucket, which is $7. But if we buy one extra piece, then the cost is $7.50 because I had to buy another piece of chicken. And if I buy another extra piece, then I go up by another 50 cents, which is going to be $8. And you might be noticing that, hey, we're going up by a steady rate, just like we did on the last problem. So I'm going to use my color coding. Here we are going up by 50 cents. At the same time, x is going up by 1. So our rate of change, which we could abbreviate ROC, R-O-C, our rate of change is going to be 50 cents, which is what the Y values are changing by, divided by 1, which is what the X values are changing by, and this would be measured in dollars per piece. So this is telling me that the chicken is costing 50 cents a piece. And of course we knew that, right? It said it right in the problem that every extra piece of chicken costs 50 cents. So that is definitely linear, because we have this steady rate of change. So let's look at the table in part C. All right, so in part C, we have a T table with 10 and 0, and 5 and 5, and then 3 and 7, and 2 and 8. And if we try and look at our rate of change, here we're going up by 5, and here we're going up by 2. And the X value is going down by 5 and down by 2. If you divide these, like check it out, if you look here, we went 5 and -5. If you divide those to find your rate of change, you get -1. And if you divide these two, 2 divided by -2 is also equal to -1. Let's try this again. Here we're going up by 1, and here we're going down by 1. Here we have another one. 1 divided by -1 is equal to -1. So we have what doesn't look to be linear right away, but if we take and plot some of these points, I'm going to go back into Desmos, and I am going to get rid of my line, and I'm going to type in this table that we are creating, 10, 0 from the book, and 5, 5, and 3, 7, and 2, 8. And look at the graph. Do they line up and form a straight line? They do. So if we wanted to find the y-intercept so that we could write the equation, that's one thing that we haven't done here, is answered all of the questions. Let's go back now. So we've done parts A, B, and C and figured out that these are all linear. And if they're linear, then the directions in the problem was more than just saying yes or no. It's saying we're supposed to graph it and find its equation. So we could now take some graph paper and we could graph each of these. So we could take, and I've got some graph paper here, so I'm going to draw an X and a Y axis. I'm going to make my X values count by 1. And the X value here is the bread. And the Y value is the fiber. Sorry, my Apple Pencil went dead, so I'm having to use something different, which is why my handwriting isn't ideal. We're going to count by 5s. That makes it fairly easy because we've got 0, 0, 1, 5, 2, 10, and we've got a nice line right here that we can graph. And we see that its slope is going up by 5. We already calculated that, and our y-intercept here is 0, so our equation is going to be y equals 5x plus 0. On our second one, we have a rate of change, and we can see our y-intercept here as well. So if we wanted to sketch the graph, now our x-axis is pieces of chicken, and our y-axis is cost, and our y-intercept is 7. So I'm going to count up here to 7. 1, 2, 3, 4, 5, 6, 7. And every piece of chicken costs us an extra 50 cents. So we're going to be going up by a half. So I know this isn't a great line because I'm going to run into my graph up here. But I do have enough to write my equation because it's always going to be the slope times x plus the y-intercept, which is 7. And the last one here, I do see that I have a y-intercept, 0, 10. So my equation is going to be y equals our slope, which we see here, I've calculated it 3 times, is -1. And our y-intercept I'm finding from the table. That's going to be 10. All right, so I am going to pull up a version of the book that I can write on here so that I can quickly find my rates of change. On part D here, I'm noticing that here we go up by 1, here we go up by 0.5, here we go up by 2.5, 5 take away 2.5 is 2.5. Here we go up by 5, and here we go up by 10. And our y values are going, or sorry, our x values are dropping by 5, dropping by 1, dropping by 2, dropping by 1, and dropping by 0.5. And if we do a rise over run, we'd have 1 over 5 for the first one, -1 over 5, we're going down, right? We've got a positive divided by a negative. And here we're going to have 0.5 divided by a -1. This, by the way, is -0.2. And 0.5 divided by -1 is -0.5. 2.5 divided by -2 is -1.25. So these are not all the same. So this would not be linear. And if we pull Desmos up and type in this table, which is the points 10, 1, 5, 2, 4, 2.5, 2, 5, 110, and 0.5, 20, we get a graph that looks a little bit more like the 1 over x graph that we were looking at before. And I think that's, you can definitely see here that it is not going to be linear, not a straight line, not mx plus b. You can see the curve when we plot these points. So how would we come up with an equation? That's an interesting topic in and of itself, and I think we'd have to play with it a little bit if we wanted to actually come up with the equation. I am noticing here that if I multiply x and y, like 10 times 1, 5 times 2, 4 times 2.5, 2 times 5, these are all equal. So if I wanted to come up with an equation, I'm noticing that xy seems to be 10, so I could write y is 10 divided by x instead of 10 times x. That's a different kind of relationship, and I wouldn't necessarily expect you to be able to come up with that equation right now. Part E, James planted a bush in his yard. The year he planted it, the bush produced 17 flowers. Each year the branches of the bush split so that the number of flowers doubles. So if I copy that into my notes, making the table that's in this situation, right, the year he planted it, which we're going to say is 0, there was 17 flowers. 1 year later, it doubled. So 17 times 2 is 34. And then the year after that, it doubles again. So doubling 34 is going to be 68. And then we double again, which is going to be 60 times 2 would be 120. So this is going to be 136. And we're not growing by a steady rate. We're multiplying instead of adding. So this is also not linear. And finally, the last table, I'm going to try and calculate slopes again. So I'm going to say here we're going up by 5, up by 5, up by 5, and up by 5, which makes it seem linear to start with because those are all steady. And this is going up by 2, up by 2, up by 2, and up by 2. So I can see that my slope is 5 divided by 2. And I can look in my table and see that when x is 0, y is -7. So my equation ends up being 5 halves x minus 7. Y equals mx plus b, where b is the y-intercept. So the last question, the last core question, you were supposed to work with your team to find one new table, one new situation that display linear relationships. Be sure to justify how you can tell that your table and situation are linear. So I am going to leave that question to you. So that is all of the core problems. Your homework assignment now is listed right here. But before you do that, I want you to fill out a learning log. These are the yellow forms that are available in the back of the room. So if you wanted to grab one of those yellow forms, in your learning log, explain how you can recognize a linear relationship in a table or the description of a situation. Be sure to include examples. Title this entry Recognizing Linear Relationships and label it with today's date. So let's grab those yellow sheets and fill out the learning logs. On Friday, we will double check this learning log. I want you to fill it out yourself. In the meantime, you can spend the remainder of this class period working on 104, 105, 106, 107, and 109. Thank you.